Thanks, Peter. Hi, everyone. Welcome to my second talk. Yeah, I sneakily started at the end of previous week for logistical purposes, but that was a Blackboard talk, and the recording is not available just yet, so I'll do a quick recap. Okay, so in the style of a TV show, so previously on cohomology of SL2ZK. So, it was quite classical stuff. So we start with a congruent subgroup of, I stick to mostly PSL2 just because it's for computational purposes slightly easier. So yeah, so I start with a congruent subgroup, and we wanted to look at first cohomology with certain coefficient systems of coming from representations of the ambient Lie group SL2R, finite dimensional coefficient systems. Just to remind you, so this is our symmetric power representation, which could be also viewed dually as homogeneous polynomials in two variables of homogeneous of degree k, the C coefficients. So the ring that we are operating over is usually indicated. It's going to be mostly either in, complex numbers or maybe some finite field. So yeah, so we argued that, I mean, this was already, this is quite well known, right? So this is kind of a a different way of looking at the so-called Manin symbols description of the cohomology of gamma. So you can just do a Shapiro lemma and work with induced coefficients at the level of the full modular group. And then you make the full modular group act on this tree that's embedded into upper half plane. Remember, a fundamental, there is a fundamental domain is a single arc with vertex stabilizers C2 and C3. This is the usual order 2 matrix, and this is the usual order 3 matrix inside PSL2Z, and the edges stabilizer is simply identity. That gives you an amalgamated free product description of your modular group, which leads to a long exact sequence, kind of a Maillard-Viatori sequence, from which you can read this description of cohomology. So I'm just doing a sketch of what I discussed last time. So this is quite explicit, and it's Hecke equivariant in the sense that the action of Hecke operators on the left can be translated to the right. That's work of Merel, Cremona, maybe even, you can say Zagier or Hecke operators on period polynomials is related to all this. And so you can implement this on computer very efficiently. But it's also, you can actually compute these space of invariance. This is essentially half of the dimension of n. This is this is 1/3, roughly speaking, and this is roughly speaking 1/2. So that what remains on the right hand side is 1/6 of the space, and you quotient out. So this tells us that the dimension of cohomology of gamma with these special coefficient systems essentially is 1/6 of the co-induced module. So in other words, 1/6 times the index of your congruent subgroup in the modular group G. So G will usually denote my modular group. And the size of the coefficient system, which in this case is just k plus 1, because it's degree k with the constants, it's k plus 1. So this gives me a rough dimension formula. I mean, it's actually, of course, can be made quite explicit, but I just want to understand the rough behavior. It's, as you can see, I'll make two observations that if you fix your lattice gamma or your level group and vary the weight, increase the weight, you'll see that the dimension grows linearly in the dimension of the weight module. And on the other hand, what you can do is you can fix the weight. So this is the coefficient system, and increase the level of your group, subgroup, and then you'll see that this is the parameter. So the dimension grows linearly, this time in the index of the congruent subgroup, which of course index is essentially the same as the volume of the associated hyperbolic twofold. Because remember, so the volume of the twofold is nothing but the index times the volume of the quotient of the modular group G. So it's just, so in that sense, yeah, so the index grows the same as the volume. Sometimes you see index, sometimes you see volume replaced in the formulas. Right, okay, so this is the classical situation. It's quite well known. As you can see, that our dimensions are growing very nicely, healthily, linearly in the level aspect and in the weight aspect. Now we want then pushed on to the case of Bianchi groups. This is the kind of, we are moving on to K equals imaginary quadratic fields with D squared free positive. I'll just say positive integer. Perhaps the easiest, of course, is just you take the Gaussian integers. Okay, so I'll use the notation that ZK is the ring of integers.
Are you
of
missing
this
a
number
minus?
field. Sorry?
Are you missing a minus in?
Yes, I am. Thank you. Right. Indeed, it's a negative, so that these are imaginary quadratic number fields. And I guess one of the simplest example is to look at so-called, these are called Bianchi groups, these SL2ZK. And if you take D equals 1, you get the Gaussian integers. And there is a similar game that you could play. These are called so-called, there's a two-dimensional CW complex sitting inside the hyperbolic 3 space on which your congruent subgroup will act cellularly. And if you take the full Bianchi group PSL2ZI, in this case, there will be a single cell as the fundamental domain of that CW complex. This is, yeah, so the H stabilizers are given by certain finite order elements, A, B, C, D. These are order 2 or 3 elements. And then, yeah, so the face stabilizers identity, and then you get these vertex stabilizers. I forgot now, D2, S3, oh, I messed it up, I think A3, S3, and stuff like that. So you can feed this geometric data into a spectral sequence, which generalizes the Mayer-Vietoris sequence that I mentioned in the classical case. And in the E2 page, it's going to stabilize if you work with complex coefficients, and you get a nice description of top cohomological dimension H2, which is similar to what we had for the classical group. Again, N is my co-induced module here. And observe that because we have a pair of complex places, we essentially have a tensor product of symmetric power representations, and the action is conjugated. Right, so we have these are the irreducible modules of SL2C as a real Lie group. These are the, so this is what we always do. We take the finite dimensional irreducible representations of the underlying real Lie group as coefficient systems, especially in connection with automorphic forms. That's what we do. So this description is quite nice. Again, you can transfer the action of Hecke operators to the right-hand side using the same procedure as Merel and Cremon. So these Heilbronn matrices, very efficient. And I'm using the fact here that it's this is Zi is Euclidean, it's a Euclidean ring. So continued fractions algorithm works. That's what you use for the Heilbronn matrices. But in general, as D grows, so to say, the geometric data that you get will be extremely complicated. So you'll have really need to automate this procedure. You can't do it by hand anymore, but it still works. You still have these so-called deformation retracts, two-dimensional CW complexes. You can still use the geometric data automated. I think that's what we did with Alexander Rum some time ago. So this can be automated. But one unfortunate thing is that, so you feel like, okay, so it's similar description. Let me just work out the dimensions of these invariant subspaces, you can individually, of course, if this is order 2, this is like half. If this is B is order 3, this is like 1/3 of the space. But the big problem is that it's almost impossible to control the size of the triple intersections. And you cannot work out a dimension formula for the cohomology from this description. And in fact, I mean, as I discussed last time, so you see that once you do some explicit computations and look at the dimensions, you feel like maybe there is no dimension formula after all. It's so erratic. I mentioned this one striking small experiment, which says that if you take, again, I'm inside the PSL2Z, so-called, sometimes people call it Picard group. I'm inside still PSL2ZI, and I'm looking at Hecke congruent subgroups, gamma naught type, with prime level. So this is a prime ideal whose norm is also prime, so it's sometimes called residue degree 1 prime ideal. And I'm computing the cohomology with trivial C coefficients. That's the simplest weight, right? And go up to norm 45,000. So you get like 5,000 or so ideals like in this range. And you compute the dimension, it's always 1. It's not always 1, 90%, it's almost all the time. Well, 90% of the time, it's 1. And you rarely see anything above 1. And this is quite in contrast. Someone's knocking at the door, so I'll just ignore the little ones napping anyways. It's big contrast because we've seen that if you do this for classical modular group, gamma naught of rational number P with H1, the index will, the dimension will be roughly speaking P plus 1/6, something like that. We just observed. So it grows nicely, whereas here I'm stuck at dimension 1 90% of the time. And I also mentioned that, of course, one of the big motivations to look at cohomology of these modular groups is connections with automorphic forms. The Eichler-Shimura isomorphism and its generalization by Günther Harder for the case of JL2 over number fields tells us that if you actually, I should put 2 here. I mean, 1 also works, but I'm sticking to 2 right now. If you look at second cohomology of gamma with, let's say, coefficient system KK, then what you're going to get is that you can actually associate this to the space of weight K plus 2 Bianchi modular forms, cuspidal Bianchi modular forms, and a small Eisenstein component of weight K plus 2 again. And I won't really go into the world of automorphic forms because they're not the really main characters here, but you can just imagine that these are some kind of smooth vector valued functions on hyperbolic free space. They have nice transformation properties and they're harmonic. We don't have holomorphicity anymore. Yeah, so if you work out the dimension of the Eisenstein part, which is easy, it comes from the cusps. If your level is prime, you have 2 cusps, and for H2, those 2 cusps will make a 1-dimensional contribution. So you see from the previous page that all those prime levels, gamma naught prime, you conclude from this Eichler-Shimura Harder isomorphism that the cuspidal cohomology vanishes. Cuspidal space of cuspidal Bianchi modular forms is trivial for all those spaces. And this is quite a striking contrast to the classical case. Okay, so this is more or less where I left off. So the dimension behavior is quite mysterious for Bianchi modular forms. So what the next thing you can do, okay, there's no dimension formula. Maybe you give up on that hope, but then you, of course, the next thing to ask is, what if I look at things asymptotically? I fix my level group gamma and then let the weight go up, or fix the level and increase the, fix the weight and increase the level, stuff like that. So asymptotic questions in those 2 directions. So let's look at those. Right, so now I'm going with a Bianchi group, and gamma is a congruent subgroup. Usually you get, as you know, for Bianchi groups, not every finite index subgroup is congruous. Actually, most of them are non-congruous. Did I say that right? I think, yeah. Yeah, so, but we'll stick to congruent subgroups where we know much more. Right. Okay. So I guess the first thing to observe is I'm going in the level aspect now. Luke's famous approximation theorem. You can says that, so if you take a nice sequence of congruence, it doesn't have to be congruence here. In this, Luke's result is more general, but yeah. So I'm going to take. I guess you start from your Bianchi group G, and then take normal subgroups gamma 1, and just go down like that. Right, and this is a sequence, and the exhaustiveness here means that if you look at the intersection of all, you get a trivial intersection. That's usually known as exhaustive, being exhaustive sequence. So the result of Luke is that, so you look at these dimensions of cohomology, complex cohomology, or you can see maybe the second beta number of the associated hyperbolic 3-manifold. And if you normalize that with the index, those ratios will converge to 0. So this means that the dimension growth compared to index growth is smaller, so that the dimension growth dominates, and then you go to 0. That's your that's what you can say. This is Luke's result, famous Luke's result. Again, for the denominator, as I said, the index grows the same as the co-volume of the volume of the associated hyperbolic threefold. So some people put here the volume of gamma I /H3. It's the same thing, right? And of course, in the last maybe 10 years or more, there has been a lot of interest in these asymptotic behavior questions, and I guess the hypotheses have been weakened a lot. And there's this very powerful notion of a Benjamin-Schramm convergence. This means that this allows for, actually, you don't have to take a sequence of one containing the other. So you can take a sequence of actually arithmetic groups, not even sitting inside the same algebraic group. So you could, yeah, so they don't have to be nested in a single Bianchi group and stuff like that. So I won't make this precise, but it's basically means that the hyperbolic threefolds that you're taking the sequence of, they converge to the universal cover. So the injectivity radius goes to infinity. But I'll just usually say that this is more or less I guess, the weakest sense of hypothesis you can impose on the sequence. I'll just usually just say a nice sequence of congruent subgroups. In the sequel of this talk, I'll just say nice sequence. Right, okay, so this says that it's dominated by the volume, but you can really pin down the exact size of growth through growth. Well, that's a very difficult problem. In the other aspect, you can fix your level and let the weight go high, right? That's the other thing you could do. So I'm gonna, again, G is my Bianchi group. So I'm fixing a congruent subgroup, and I'm taking my coefficient system. Remember, these are the irreducible representations of SL2C as a real Lie group. So these are homogeneous polynomials in 2 variables of degree K. I'm testing that with another copy. I'm taking the parallel weight here because of Fu's result, but I guess in general, you can, of course, you don't have to take them the same, but I'll take the same. And then the action of, if you take an element of the group, it acts on the 2 copies in a conjugated twisted way. That's the bar in the second. It uses the 2 embeddings, your pair of complex embeddings for the two actions. Right, so what happens here if you just fix the level and the weight go up, get bigger and bigger? So this is a very recent result, actually. Fu talked in the Cohomology seminar, because 2 months ago or something. This is announced. It's not actually printed yet. It's on the archive for 2 months or so. And the result is actually confirms a conjecture that has been perhaps experimentally also supported and so on. So the result is that if you do that, fix the level and let the weight go up, the dimension of H2 will grow linearly in K. Well, just observe that the dimension of this weight module as you can see, there's 2 copies of symmetric k power. So it's going to be k plus 1 squared. So in other words, asymptotic is k squared. But the dimension grows linearly in k. So you're looking at the square root of the dimension of the weight module. Observe that in the previous case, in the classical case, the dimension grows linearly in the dimension of the weight module. Here is the square root of the dimension of the weight module. So it's, and this is really tight in the sense that you don't really expect anything smaller because smaller than that, the square root, because you can see in nice cases there is this base change functoriality. So if you start with a classical space of modular forms gamma naught with level n, an integer, weight, some fixed weight, base change functoriality of Langlands basically gives you a linear map to the space of Bianchi modular forms with level given by the ideal generated by that rational number n. So this is classical here and Bianchi on the right-hand side. This is Bianchi. And, you know, if you pass to cohomology using Eichelor-Shimura isomorphisms, so we know that the left-hand side grows linearly in the weight. So that means that there's an input, there's a part of cohomology, this is called the base change part, that grows linearly already, coming from smaller algebraic groups of classical modular forms. So that already gives you a lower bound of growth, a linear lower bound coming from base change. And Fu basically says that this is tight. So this is actually the true growth. So this means that whenever you have base change functoriality, whenever you have a base change part, that's more or less, you should expect it to give you everything. So generically, your Bianchi modular forms are made of base change. And you could see that in computations, going back to Grunewald, Finis, and Tirao paper that, and then with Alexander, we extended some computations like that, that it's mostly base change, those spaces. Right, so this is the asymptotic results in the level and weight directions for Bianchi groups. So this is, again, this is quite an improvement, just a recent paper of Fu. Now, I'm going to go back to something we discussed last Friday. This whole business relationship with Galois extensions of number fields. So a certain some type of non-abelian class field theory approach of Langlands functoriality. Right, so last time we mentioned that if you take a classical modular form, let's say CAS form, it has an elliptic representation, fix your prime L. That elliptic representation will fix because the left-hand side is complex, it's going to fix a lattice. So fix that lattice inside the elliptic representation and reduce modulo that lattice, and you get that mod L representation. That mod L representation cuts out a Galois extension of Q, whose Galois group obviously injects into GL2 FL bar, some L power. So that in that sense, your classical modular CAS forms were cutting out non-abelian extensions of Q, right? So you expect a similar thing going on in this imaginary quadratic situation. And so here is, if you just do naively reproduce that schematic here, that picture, on the left-hand side, I have Galois extensions of my imaginary quadratic field K, that's fixed, various Galois extensions L, such that the Galois group injects, it comes with an injection rho, into some GL2FQ, Q is an L power, fixed prime L. And you expect that, you know, if you start with a cuspidal Bianchi modular form, you have nice elliptic Galois representations built in the 90s by Taylor and Harris, Taylor, Sudri, and other people have extended those results and whatnot. And you take the elliptic representation, reduce mod L, and it should give you an extension like this. So this is the going from left to right. So this is Taylor and others. So this is all well known. These elliptic Galois representations exist, and you just reduce them mod L. That's, in other words, you're really looking at a cuspidal Hecke eigenform, Bianchi modular form. You're looking at its eigenvalue system and looking at the mod L values of that eigenvalue system. So that's the left-hand side. And on the right-hand side, this is kind of a Serre's conjecture direction, right? Serre's modularity conjecture. You want to ask if everything on the left is parameterized by one of these Caspidal-Bianchi modular forms. Well, it turns out that actually, in our case, this worked for classical modular forms, right? Serre's modularity conjecture is proven and everything. But in our case, it doesn't quite work because, in a sense, the left-hand side is too big for the right-hand side to parameterize all. There are some heuristics in the style of Bhargava carried out by Bergerano and Venkatesh that kind of gives you a some kind of feeling of the left-hand side and the right-hand side. And we already saw the right-hand side is actually small. Bianchi modular forms, there's a paucity. They're not as many as you see on the classical modular forms. Whereas the left-hand side is actually quite big. So that excuse me. So that means that the right-hand side is not quite the what you want to put on the right. And it turns out the correct thing to put on the right-hand side is not just mod L reductions of Hecke eigenvalues of Caspidal Bianchi eigenforms, but eigenvalue systems captured directly in mod L cohomology. So if you want to look at it this way, so remember, so these eigenforms through the Eichler-Shimura harder isomorphism, they are captured. You already have the this space of Caspidal modular forms. They live inside complex cohomology. We already, okay, so with special weight system. So they live inside complex cohomology. So you're really, in a sense, you're saying that I take Hecke eigenvalue systems captured in complex cohomology and taking mod L reductions of those. And what I'm now proposing is that, well, don't take complex cohomology and reduce to Hecke eigenvalue systems mod L. Start directly with mod L cohomology and look at the eigenvalue systems captured there. And this turns out to be the right thing to do. And there are a lot of eigenvalue systems in mod L cohomology that do not really come from reductions, mod L reductions of eigenvalue systems of automorphic forms. So the right-hand side is, I'm going to talk about that now. So if you put it this way, and basically forget about automorphic forms, but put mod L cohomology on the right-hand side. Now, how do you even go from right to left? Well, that's the famous result of Scholze. Guarantees that any eigenvalue system captured on the right-hand side will have a mod B-Galar representation cutting out something like that on the left. And now the modified version of Serre's conjecture goes this way. Serre's modularity conjecture is now something that lands in cohomology, mod L cohomology, as opposed to space of Caspidal Bianchi modular forms. And why is the right-hand side much bigger? What could really, if the eigenvalue systems here are not coming from mod L reductions of automorphic forms, Bianchi modular forms, where are they coming from? That brings us to the torsion cohomology. So here's the class, this basic picture. I'm just going to stick to trivial weight here for convenience, but this also works with higher weight modules with nice lattices stabilized inside those weight modules. But let's stick to trivial weight. So I've got my second cohomology, integral coefficients. Now, because gamma is arithmetic, general reduction theory tells me that this is a finite generated abelian group. So it has a torsion part, finite torsion abelian group, and some copies of Z. And the rank here will be second Betty number. Yeah, some rank. Now, if you take this abelian group and tensor it with complex numbers, you kill all the torsion, but the image will be a lattice sitting inside the right-hand side, right? So you land, by killing all the torsion, you land into this world of automorphic forms here. This is automorphic forms, complex cohomology. But if you just look at the standard mod P, says if there's a standard long exact sequence that tells you that, the tensoring by FP bar, I should maybe have said FL bar, but anyways, is surjective. So by tensoring with FP bar, you surject onto the mod P cohomology. Now, as you can see, any eigenvalue system captured here will give you an eigenvalue system through reduction here. There's no direct map here, but I'm talking about eigenvalue systems. So mod L reductions of all the automorphic data already appears here in mod P H2. But the point is that if you have P torsion, if there's possible P torsion, that's going to give you an extra class and it's going to survive through tensoring with FP. All the other torsion, of course, will be killed, but if there's P torsion, that will survive. And the whole point is that, yeah, so you can have, if you have extra P torsion here in this torsion part, you're going to get things that are not coming from automorphic forms, possibly. And it turns out that there's lots of torsion. And that gives us lots of eigenvalue systems that are not coming from automorphic forms, so to say, through model reduction. That's the very mysterious thing about Bianchi group situation. You have lots of torsion. And when you look at mod P cohomology, you see eigenvalue systems that are not coming from complex cohomology, at least at the same level, when you look at the same level. Right. This brings us to the Bergeron-Venkatesh conjecture. Actually, I'm telling the story kind of in a reverse order. Bergeron-Venkatesh were looking at the growth of torsion. There's lots of torsion. Then this should mean that there should be lots of these special type of Galois extensions on the left. So they want to use the heuristic to confirm their expectation that there should be lots of torsion. So I'm kind of telling you the other way in a kind of reverse storytelling. But anyway, so explicit computations going back to 70s to Fritz Grunewald actually already revealed that there is some, you can observe some large torsion, maybe 5 torsion, 7 torsion, stuff like that, that you don't see in the classical modular forms. In the modular forms for classical modular groups, there is 2 or 3 torsion at best, which comes from the 2, 3 or finite order elements. But here you see torsion, 5 torsion, 7 torsion in the homology or second cohomology, and Bianchi groups only have 2 or 3 torsion. So there are some, you see some large torsion, and that was what Fritz Grunewald was kind of intrigued about. And you can, also more recent computations, machine computation shows you that actually there is tons of, there's lots of torsion, and you can see actually astronomic primes dividing that size of that finite abelian group's torsion group. It can get really, really big, really fast. And the conjecture of Bergeron-Venkatesh actually tries to tame this very wild situation. So again, I'll just be kind of vague here. If you take a nice sequence of congruent subgroups, let's say gamma I, again, the best hypothesis is the Benjamin-Schramm convergence sequence. Then what you do is you take the sequence of nice congruent subgroups and you look at the second cohomology, let's say with trivial Z coefficients, and you look at the size of torsion. I'm going to take the ln of it, which means there's something exponential going on. If you normalize that by the volume of the associated threefold, these ratios here, these normalized size of torsion, as you go down the sequence, it converges to 1/6 pi. So this means that there's an exponential growth, right? The size of torsion grows exponentially compared to the volume, with the volume. This 1/6 pi is related to the so-called L2 torsion of the hyperbolic free space, the ambient or the real Lie group behind. So this is conjecture of Bergeron-Venkatesh, and they. Yeah, so originally they worked with, they also proved things in the paper, in their well-known paper. They work with, in their proof, the things that prove are about co-compact arithmetic groups acting on hyperbolic free space, because their methods are analytic, so-called Cheeger-Müller theorem. They try to get a hold of the size of torsion using the so-called analytic torsion. And so there's this topological torsion equals analytic torsion business. And of course, when your manifolds are not compact, the analysis gets extremely difficult. So they stick to the compact hyperbolic free, arithmetic free hyperfolds. And also there's another complication coming from the type of coefficient system that you use. The results are for strongly acyclic type of coefficient systems where there's a kind of spectral gap that lets you, again, analytically, you have much more control over these kind of coefficient systems. So trivial Z coefficients is not one of those coefficient systems. But you should think more of in terms of our two variable symmetric power, tensor symmetric power representations, coefficient systems. Essentially, you're looking at non-parallel weights. Yeah. Right, so this is the well-known Bergeron-Venkatesh conjecture. This is a special case of hyperbolic free space or Bianchi groups. And there's very strong numerical evidence that supports this convergence. Actually, it's quite striking. And in the other aspect, you can again, what time is it? Okay, I still have some time. You can do the, again, same thing, fix your level, let the weight go up and work with a lattice inside your weight system. So you can still have an integral cohomology, but higher weight. And so you can ask about torsion there. What's going on with the torsion there? So this question has been looked into by Müller very soon after the Bergeron-Venkatesh paper came up. And with Müller and Marshall, Simon Marshall, they proved a result, again, using the co-compact arithmetic lattices acting on hyperbolic free space. Again, because there are analytic difficulties going beyond compact ones to non-compact ones with cusps. But you can just, it's safe, numerical data suggests that it's safe to take the result that's for co-compact arithmetic groups and generalize it to Bianchi situation. So the result would look like this. Take your congruent subgroup sitting inside the Bianchi group, say, and take any kind of non-parallel weight, but I'll stick to, because I'm putting a specific number here on the right, which I took from their paper, I'm going to stick to the same kind of weight system, an even number, comma 0. So it's essentially one copy of the symmetric power representation with an even degree. And I'm putting some integral lattice in that coefficient stabilized by gamma, so that it's an integral cohomology, and there's torsion in there. And the result is that, the conjecture is that the torsion varies exponentially with respect to k squared times the, well, it's actually exponentially with respect to the volume, and there's a specific actual limit here, log of the torsion divided by k squared. K squared is, it's square of the dimension here, right? Times the volume of the manifold. It converts to 1 over 2 pi this time. Again, there is the L2 torsion is playing a role here. Right, okay, so we have exponential growth in both level and weight directions here. That's the upshot, with very specific constants that limits exist, positive limits. Now, I'm going to move slowly towards the general number field situation. Times it. Okay, so I got essentially 10 minutes or so. It should be enough. Any questions so far? This is the thing. Yeah. Okay, you let me know if you have a question. Please jump in.
Is there a question? Sorry.
Peter, is there a question?
Is there a question?
I heard some.
No,
I heard
there is
something.
no question here. Is there? No, there's no question here.
All right. Okay, so now that's the Bianchi situation. Bianchi was, in a sense, the most intriguing GL over number field case, you could say. And now I'll see. We're going to see why. Now, now I'm going to take a general number field with signature RS, meaning R is for real places, real embeddings, and these are complex pairs of embeddings. And I take a congruent subgroup inside the modular group SL2ZK. So this sits as a lattice inside a bunch of copies of SL2R and a bunch of copies of SL2C. as such, it acts, you need all of them to get a lattice, otherwise you don't really get, the image won't be lattice if you don't get all of them. And it's going to act properly. This is a nice action onto this product space of R copies of upper half plane and S copies of hyperbola 3 space. So that the quotient here has a nice finite volume remaining 2R plus 3S fold. It's not gonna be compact because we have parabolic elements. So, right, okay, again, we have the, of course, Harder's Eithler-Shimura isomorphism, which connects these kind of cohomology of gamma with coefficients coming from the finite dimensional irreducible representations of the ambient Lie group, which are that product Lie group. So this bold K here is tensors of the symmetric power representations. For each real one, you have some degree here, and for each complex, you have a pair of degrees, so to say. It's hard to, I won't get into all those notations and stuff, but you should think of the, so symmetric powers, several degrees bundled up together. Okay, so these spaces, again, the important thing is that I'm taking complex cohomology here. It can be accounted by various spaces of automorphic forms. These are the automorphic forms that are known as cohomological, right? They are GK cohomology is non-vanishing at infinity, these automorphic representative forms. So these are kind of, it's a very nice class of automorphic forms. You don't, of course, see things like mass forms or limit of discrete series type of things, but still, it's a very nice class of automorphic forms. And we know through representation theoretic results that cuspidal type of automorphic forms, these are that vanish at cusp, they contribute only to a kind of a middle strip. This is a very general result that if you apply to our situation of SL2 over a number field, I think it should be like this. You start from degree R plus S, and go all the way up to R plus 2S. This is the middle strip. That's where the space of cuspidal guys contribute to. Actually, the contributions into various, so the same guys contribute to each of these guys with different multiplicity. Actually, it's a little bit complicated. But for SL2 over number field or GL2 over number fields, I recommend Hida's papers from 90s, which made Harder's automorphic representation theory language investigations, developments quite in the classical language. It's quite tedious, but it's all there. Right, so this S here, as you can see, plays a vital role, right? Or pivotal, maybe is the right word. Its critical role is played by this number S, which is the number of complex places. So in a sense, if you're interested in Hecke eigenvalue systems and automorphic forms, connection, long-length program type of things, you want to really look into the middle strip. But of course, different people are interested in different degrees. Peter would be interested in more extremities of this whole range. Right, okay, so some easy observation is that
Haluk, can I ask a quick question?
Yes, please.
So you're saying there's cuspidal cohomology for if you take SL and Z just the integers, only in degree 1, R equals 1, and S equals 0?
S equals 0 and R is equal to 1, you're saying. So classical modular form.
Yeah.
Yeah, because it's a surface.
Oh,
right?
I'm sorry.
Yeah.
I'm sorry. I forgot that we are in n equals 2 case. So for larger n, this would be bigger.
And what is n?
N is the rank of the matrix.
Oh, you want SLN?
Yeah.
SLN.
Yeah.
Yeah. So for SLN, these numbers can be directly calculated. Actually, I just recently double checked this with a nice survey paper that one of my main go-to ones, Jianshu Li and Joachim Schwärmer. They have a nice survey paper in a Chinese journal, or I forgot what journal actually, but it's from the 90s, which gives you explicitly, actually, they compute what this numbers are. They have a general formula and then make it specific for the case of SLN. You can find on page 5 or something. But again, the idea is the same. There's a middle degree. If you work with GLN over number fields, essentially tempered and cuspidal, they are the same thing. So this range actually is the contribution of tempered things, which happens to be the same as cuspidal. But if you go to beyond GLN to different kind of classical groups, you can still have cuspidals at even very small degrees, but the tempered will be focused on the middle strip. So there's a famous example of Pietetsky, Shapiro, and Roger Howe, which give you cuspidal but non-tempered things in actually degree 1. For what's the group there? I forgot what the group is, but some orthogonal group. Yeah, but for your question for GLN, yeah, there's a middle strip, and the cuspidal guys will only contribute that middle strip of length given by the deficit fundamental rank here, which happens to be S. But yeah, in this paper, actually, maybe I can send you the paper because I hand scanned it, so you may not maybe find it online. It's quite made explicit. Does it answer your question?
Thank you. Yes, thank you.
Okay. All right. So yeah, just observation is that. So okay. So in general, since it's a whole computational meeting, right? Computing these degrees is difficult unless it's small. And when is it small? Essentially, when it's the classical modular group or a Bianchi group. This is what I covered. If you want to go beyond that, even for real quadratic, meaning like 2 real places and no complex places, then it's a 4-dimensional manifold, real manifold, and you need to look at H2, the middle degree. It's really difficult to compute it. And the only direct way, as far as I know, is what Paul and Don and so Voronoi method is the way to do it, which will be explained by Paul and Philippe. So just make sure if you're interested, check out their talks. I should just mention that if you're interested, I mean, of course, you can say, I want to compute that cohomology group, then okay, then it's tough. You have to use Voronoi method. But if you say that I'm interested in Hecke eigenvalue systems captured in that degree, well, then you might cheat. And there are different, there's functorialities. Langlands functoriality means that different algebraic groups, if they're structurally related, their automorphic forms will be related. So you can use like Jacques-Langlands correspondence to, in some situations, get your Hecke eigenvalue information from a kind of a smaller dimensional manifold. Sometimes you can do algebraic modular forms. So this is actually a 0-dimensional manifold. If you're lucky, that's what Lassina Dembele does a lot. Or you can do, instead of computing with a real quadratic situation, you can do Jacques-Langlands and compute a Shimura curve, for example. That's what John Voigt implemented that's how Magma computes classical modular forms, either algebraic modular forms or a Jacques-Langlands correspondence to a Shimura curve. But directly computing those degrees is difficult, especially Hecke operators is even more difficult. I think Paul and Philippe will explain all that. Now, again, I'm talking too much, but is it 50 minutes or 1 hour, these talks?
1 hour.
Okay, good. I think I can wrap it up in 10 minutes, yeah. Now, the conjecture I shared with you of Benjamin and Venkatesh for Bianchi groups, actually, it's a very general conjecture for general semi-simple groups. So it also works for our SL2 over number field. So if you specialize, so the general idea is that your semi-simple real Lie group will have a so-called deficiency, so it's an invariant, sometimes also called fundamental rank. In our case, it happens to be the number of complex places. And that number invariant should determine the behavior of torsion or general behavior of cohomologies, roughly speaking. So here's what you expect. If your deficiency is 0, then you expect very little torsion. And in fact, you expect lots of cohomology. Think of classical modular forms here, right? And what's going to happen is that any kind of extra eigenvalue systems maybe arising from the torsion will be absorbed, will have lift to a complex eigenvalue system. So in other words, all the arithmetic data is really coming from modular forms here in this situation. The next situation is this deficit one. This is our complex place one situation. Here you expect lots of torsion, just in the case of Bianchi groups, and little complex cohomology. And that's exactly what we see in Bianchi groups. And in the case beyond that, it's a little bit of both. It's really hard to make precise, but that's the heuristic. And to make this more precise, they have a more specific conjecture that kind of leads to the previous heuristic. So this is again applied to our SL2 over number field case. Take a nice sequence of congruent subgroups, Benjamin Schramm convergent or whatever, or maybe exhaustive normal sequence. If you're more conservative, then you look at the degree K cohomology and torsion in there, and normalize it. So take the log of it and normalize it by the volume. So this limit will exist for every degree K, and actually it's going to be 0 unless, this is the magic configuration, unless your deficit is 1, you have one complex place, and you really hit your degree of cohomology, which is an integer, mind you, hits that right-hand side. So the right-hand side, this dimension of the symmetric space X plus 1 divided by 2, that needs to be an integer. And if you are at that middle degree, and if your deficit is 1, then you expect a positive limit, which actually they specify what that positive limit should be. It was 1 over 6 pi for the Bianchi case, if you remember. It has to do with the L2 torsion, analytic torsion. So this is it. So they say that essentially most of the time you expect less than exponential growth, but when you hit that middle degree in the deficit 1 case, you see exponential growth. There's a positive limit there. Right, and I mean, the original conjecture again is in the slightly more conservative case of co-compact lattices, where analysis is a little bit better understood. But I guess at this day and age, you expect this generally, and this is still Bergeron-Venkatesh conjecture. And finally, I should also say a little bit about dimension growth for this more general SL2ZK setup. Now, we already observed that when your K number field is totally real, so that you have no complex places, S is 0, really the strip that cuspidal modular forms contribute to is only a single degree in the middle. That's the degree HR, is the only degree that they contribute to. So there is a single degree of importance in the middle. And the good thing about this totally real case is that the quotients are maybe after some kind of compactification, they're complex points of some projective algebraic variety. So you're in a Shimura variety situation. So that's quite good. You have a lot of tools from algebraic geometry like Riemann-Roch, or even perhaps you don't even need to go to Riemann-Roch. You could say that in this case, when it's totally real, you're going to have discrete series representations. Those are the essentially components of automorphic representations at infinity. And trace formula methods, they pick up a discrete series because they're isolated in the spectrum, in the tempered spectrum. So you can use trace formula methods to get a really dimension formula. In practice, that dimension formula will be extremely difficult to make practical. You can actually, another recent cogent seminar by Frederick Stromberg, Frederick made that dimension formula for, in the case of real quadratic fields, he may try to, because it has a lot of explicit terms that needs to be computed and it's not easy to compute. So he made that explicit. He has this program that kind of works that. But in theory, you have a dimension formula. And from the dimension formula, you can read the following. If you fix your weight and take a sequence. So the dimension then grows linearly in the volume of gamma or index of gamma, just like classical modular forms, which actually is a particular case of total real, right? The simplest total real field. And if you fix your level group gamma and let the weight go, then you're gonna grow, the dimension will grow steadily with the dimension of, basically linearly the dimension of the weight module, whatever that weight module is, tensor of symmetric powers. So it's gonna be something like k to the r, right? And this, I think, as far as I know, it's first observed maybe by Shimizu, again, by trace formula kind of things. Right? Yeah, so we have very healthy, ample growth of complex cohomology grows linearly in both index direction and in the weight direction, just like in the classical modular forms. And more generally, it's very difficult to understand the dimension growth. What you can say, this is a recently announced paper of Nikolai, Sebastian, and Jean. It's a very general result. I'm taking a special case of it. It could be that maybe for asymptotic number fields, maybe what I'm displaying here maybe was already known. I'm not quite sure about that. Maybe some experts can tell us, but their recent result looks just like this, but in a special case, it reads this. So if you take the, let's say, it's about beta numbers, so probably you could generalize it to certain coefficient systems as well, but let's stick to trivial C coefficients. If you take a nice sequence of congruent subgroups in SL2ZK, or it could be even a general Benjamin-Schramm convergence sequence, and you want to look at trivial kth degree cohomology with trivial C coefficients, the dimension of that divided, normalized by the volume will be, will converge to 0, so dominated by the volume growth, unless your S equals 0 and you're in the middle degree. So otherwise, you see this captures, this is of Haluk's approximation theorem that I showed for Bianchi groups is a special case of what is displayed here, but it's a more general phenomenon. So, and we already know that when S equals 0, so total real, and you're in the middle degree, we already saw it in the previous slide, you have a nice positive linear growth in the volume, right? So that's a positive, there's a positive limit. But otherwise, the limit is 0, it's dominated sublinear in the volume. And what's the true growth? That's a very difficult question. Again, the same question, but you fix this is kind of the level aspect. If you fix the level group and let the weight go, what about the dimensions? What's happening with the dimensions there? What's known is by just some trace form, the kind of thing is, again, when beyond the total real fields case, where we know what happens, if S is not 0, so if your K is not totally real, then what is known is it's a little of the dimension of the weight module. So it grows slower than the dimension of the weight module. Remember, in the Bianchi case, it grows like the square root of the dimension of the weight module. But what we know from trace methods is that it grows slower than it's sublinear than the dimension of the weight module. What's the true growth? It's again a very difficult problem. As I said, Fu has this new paper where in the Bianchi case, he shows that it's exactly 1/2 the true growth, the square root of the dimension of the weight module. But he has also some improvements, I guess, latest for general case over SL over number field. He has some improvements. It's sublinear, but he has some power improvements, I think. But I'll just refer you to Fu's paper. And I'll stop here. Thank you for your time. I'll right on time. I've never done that before. Peter, this is where you say thank you, Haluk.
Thank you, Haluk. Are there any questions for Haluk? Possibly also on Zoom. If you have a question on Zoom, please write that into the chat. I have a question. Can you go back to the conjecture by Venkatesh and I forgot Bergeron? Yeah. So this is only for, again, for SL2 of SL2. Is that right?
Well, I made it for SL2 just because there's these specific numbers here. But in general, you will just say that if the deficit is 1 fundamental rank, and this is a dimension of the symmetric space plus 1/2. Yeah, otherwise, if you make these replacements, that's the full conjecture for semi-simple real Lie group and nice sequence of congruent subgroups. That will be the conjecture general.
And I mean, is this known for any special cases yet? Is this known for, I mean, obviously for k equals 0, this is known to be the limit 0, because then it's just z. But is it like, for example, for the cohomological degree, I think that's like 2r plus 3s minus 1. Is it known there?
I'm not sure. I think there's this recent paper of these 3 guys that I mentioned here, Fratzig, Hurtado, and Rambo. They do, if I understand, I haven't looked at detail, but I think they do perhaps tell you sublinear in the volume, sub-exponential in the volume for degrees that are outside this, I think. I'm not quite sure.
But I mean, oh, sublinear. Okay.
So yes, so this would go to 0 in the degree that's not specified here, the configuration specified here. But
if you forget about the logarithm.
No, I mean, you always have the logarithm. You want either the question is if it's exponential with volume or sub-exponential. I think that's the question here. Yeah, and I think in the other degrees it's sub-exponential. I think I think their result implies that. But I must say that don't take my word on it and check the paper.
Okay, thank you.
Maybe someone else knows it from the audience.
I will ask. Is there any other questions? If there is not, let's thank Haluk again.
Thank you very much.